Hey everybody, it's Mrs. Slauson, and we are starting chapter 3. So we have moved into those really big packets that I gave you before we went to remote learning. And you need the pink one, and you need to start on page 40. All right, so I know that's weird that it starts on page 40, but this is a continuation from other packets. So what we're going to be talking about in chapter 3 are square root and cube root functions. And if you're going to notice in our very first section, we're going to talk about inverses, because square root functions and cube root functions are the opposite or the inverse of the functions from our last chapter in chapter 2, which were squared, something squared, a quadratic, so a second exponent, and a cubic function, so we saw a third power. So this is just the opposite. So our first section is really going to just kind of dive into what inverses are. So you already know about inverses, like adding has an inverse of subtracting, dividing has an inverse of multiplying, etc. So here we're just going to look more at inverse functions, okay? So back in Algebra 1, you learned that if you have a set of ordered pair, that is called a relation. And then some relations get to move on and become a function because when we graph those ordered pairs, they pass the vertical line test. And then in Algebra 2, we learned that some of those functions get to become one-to-one functions because then those points pass the horizontal line test, all right? So every relation, so every set of data, x and y points, has an inverse relation. And an inverse of a relation is a relation that just undoes the relation. So again, like multiplying undoes division and adding undoes subtraction. So if the inverse of a function, so we got a function, we're going to call it f of x, is also a function, then instead of using f of x to show that it's the inverse of it, we're going to write it like this. So you're going to see this little -1 that looks like an exponent. But it just means if f of x is the function, then this is the inverse of that function. So let's just start to take a look at what this means. Now, the next thing it says, if the inverse of a function is not a function, then we don't get to use this notation. So just because it's a function doesn't mean its inverse will be a function. It'll still have an inverse, but the question is, does the inverse also get to become a function? So starting here, you're going to notice we got our relation, so just a set of ordered points. I could also write them like this, so 0, 7, 5, 3, and 6, 2. And I remember this because, remember, domain is typically the x, and your range is typically the y. Let me move this up a little bit more. So in the inverse, we start to undo things. Everything just becomes the opposite of what it was. So what was the domain in our relation, when I look at the inverse, will become the range of the inverse. And what was the range of the regular relation will become the domain of the function. So now 7 as x gets 0 as y, and 3 goes with 5, and 2 goes with 6. So if I wrote this as an ordered pair, it would be 7, 0, 3, 5, and 2, 6. All right, so the next thing we're going to look at is, again, just what's the domain, what's the range. So the domain here, just in numerical order, is 0, 5, and 6. And then this domain becomes the range of the inverse. And then the range of this function, so we have the values of 2 and 3 and 7. This range becomes the domain of the inverse. So essentially the x's and the y's swap roles. All right. So now what we want to see is this set of data, these ordered pairs, is this a function? And it is, because in a function, remember, an input can only have one output, or you should never see x repeat. And I never see x repeat here. This input 0 only has this output of 7. All right, so is this a function? Yes. So since it's a function, I could actually give it that function notation, f of x. So now what we want to see, is this a function? Is the inverse a function? It's still an inverse, because I've just undone everything that was done. But when I look here, does x repeat? No. Does each input only have one output? And that it does. So that means that this is a function. So if this is f of x, then this set of data would be represented, and I just put a little -1, like an exponent, but it just means the inverse. So let's try that again. Let's look at the second bottom set. So here I've got my data. So again, just writing it as an ordered pair. I've got 3 with 0. I've got 7 with 5. 1 with 5. That's what this is saying. And 4 goes with 1. So again, my domain are just these. I'll just put them in numerical order. So I've got 1 and 3 and 4 and 7. And for my range, I'll just put those in order as well. So I've got 0 and 1 and 5. So my main question is this data, sorry, I got my dog getting in a bag over here, is this data, that's a relation, a function? And it is not, or sorry, it is, because all the x's are different and each input only has one output. So this is a function. So I'm going to call this one g of x just to get a different type of function name. So now what we're going to do is find its inverse. All right, so writing this, just switching it around, 0 would go with 3, 7 would go with 5, 5 would go with 1, and 1 would go with 4. And if I just map this, again, 0 goes to 3. If, let's see, I think some of these are switched. Nope, it's not switched. I messed up. So I'm going to find my little white up tape. I didn't switch these two around. Let me fix that. Sorry about that. 5 gets 7. 5 also gets 1. So that right there is saying to me that the input of 5 has 2 outputs, and that can't happen. And then 1 goes with 4. So again, my domain is this one's range. And this one's range is this one's domain. And is the inverse a function? Again, it is the inverse, but the answer is no. It's not a function because this input of 5 has 2 outputs. So it would not pass my vertical line test. Okay? So where this is g of x, this does not get the g with the -1 of x. All right, so a couple things to really take away from this page. F of x, so a function f, only has an inverse. So it gets this name if it's 1 to 1. All right? So if a function is 1 to 1, then when you find its inverse, it gets to have this special function notation of the -1. If it's not 1 to 1, then the inverse is not a function. And this just says that the domain of f becomes the range of its inverse, and the range of f becomes the domain of its inverse. So the x's and y's switch spots. Okay? All right, let's jump to the next page. So the next thing we're going to take a look at is how do you actually find the inverse? And we're going to take this idea that x and y switch spots. So using the above facts, so the pages from the page before, we can find the inverse by interchanging x and y and then solving for y. So the first thing I'm going to do is take f of x and just replace it with y. And this is a function. I know it's a function because it's f of x. So what we're going to do is we're going to find the inverse of it, and then we're going to see, is the inverse actually a function? So the first step of finding an inverse is we're going to have x and y switch spots. And then if you remember, a function is when it's y equals everything else. So that means I'm just going to get y alone. I'll be moving that 1/2 and that 1. So the first thing I'm going to do is move the 1. So I'll subtract 1 to the other side, and it becomes x minus 1 with this 1/2 of y. And then to get rid of the 1/2, I multiply by the reciprocal. And half of 2, when you multiply that, is 1, and then 1 times y is y. And then I'm going to take the other side, the whole other side. So I'm going to wrap it in parentheses, and I'm also going to multiply that by 2, and then I'm just going to distribute that 2 in, and you get 2x minus 2. So now we're going to see, does this y get the inverse notation of f of x? So we're going to do that by seeing when we graph it if it passes the vertical line test and the horizontal line test. But let's start by graphing the original one. So 1/2 x plus 1. So here's my y-intercept of 1. And then this is my rise 1 over 2. This is a positive slope, so it should be going uphill. So I go up 1 and over 2. And I'm just going to keep repeating that until I get a lot of points on here. And connect them. All right, so I'm just going to remind myself that this line represents f of x. It's not only a function because it passes the vertical line test, but it's also a one-to-one function. And if it's a one-to-one function, then its inverse should be a function. It should be. So let's just verify that. So now I'm going to graph this one. I'll go to my y-intercept of -2, and I'll go up 2 over 1, and I'm just going to repeat this pattern as I do that. And this is a function because it passes the vertical line test. As it also so happens, it's a one-to-one function, but I don't really have to worry about that. So this blue line now can become f-1 of x because it is officially a function. It passes the vertical line test. And that means I could write it over here like this. So again, I knew that that was going to be a function because the original function was a one-to-one function. All right, so let's try one more. So here we're just going to find the inverse, 3/2 x minus 6. So the first thing I'm going to do is just change this to y. And then the second thing I'm going to do is switch x and y around. And now to make it a function, it has to be in the format of y equals. So I'll be moving the 3/2 and the 6 over. So again, I'll move my addition over, so this becomes x plus 6. And now to get rid of 3/2, I'll just multiply by the reciprocal. And that becomes 6 over 6, which is just 1, and 1 times y is y. But then I'll multiply all of this side by 2/3 as well. And I'll just put that in parentheses so that I can see it's multiplying the whole thing. And then I'll distribute. So here I get 2/3 x. And if you just kind of go off to the side, what is 2/3 times 6? So I'll put it as 6 over 1. Well, that's just 12 over 3, and 12 over 3 is 4. So let's graph these. So here was the original function. Here is its inverse. We're here to see, is the inverse a function? So I'm going to start by graphing the original function. It's another line. So there's -6, and I'll go up 2 over 3. And again, I know which way to go over because this is a positive slope. All right, so there's my original function, and I'm going to call that g of x over here. And not only is this a function, but it is a one-to-one function. And since it's a one-to-one function, that means its inverse, this, should be a function. So right away, I know that I can replace this y with this. I don't even have to see it graphed. But we're going to go ahead and graph it. So here's my y-intercept of 4. And I'm going to go up 2 and over 3. And I just repeat this pattern and get as many points as I can on there. So that's pretty good. Okay, and then this gets the name of an inverse function. So I put that g with the -1 of x with it. All right, next. So what if you're given a function and what is supposed to be its inverse function? How do you verify that it's an inverse? And so we're going to go back to what we learned in chapter 2 of these things called composition functions. So what we're going to do is we're going to take these two functions up here. We're going to work with g of x and its inverse. So I'm just going to rewrite them here. So g of x is 3/2 x minus 6. And its inverse, which, all right, let's see, I don't have a lot of room here. Let's put it over here. Is 2/3 x plus 4. So if you remember, and this was in our chapter 2 test, I suggested when you see all these parentheses that you start with the outer set, really make them big, and go to what's in here. And this means I should go to g's function and put a 6 in here. So imagine, I'm just going to write with a pencil over here, 3/2 times 6, which is just 3/2 times 6 over 1. So when I multiply that, I get 18. And 18 over 2 is 9, and then 9 take away 6 is 3. So when I'm done, this g of 6 is worth 3. And I know I did that all in my head, but there's not a lot of space here. So I'm going to replace this g of 6 with the 3 that it's worth. Okay, so again, I put 6 in. 18 over 2 is 18 divided by 2. That's 9. 9 take away is 6 is 3. And now this says go to the inverse, or what's supposed to be the inverse function, and put it into here. And so I'm going to do that. So I'm just going to take my pencil. I'm going to put a 3 here. Put it over 1. And 2/3 times 3 is the same as 6 over 3. 6 over 3 is 2, and 2 plus 4 is 6. All right, let's try the next one. So I'm going to switch colors here. So again, I've got this really big outer set. And this says I should go to G's function. And this time I'm going to put -4 in here. So I'm going to erase this just so you can see it. And I'm going to multiply. So when I multiply this fraction, I get -12, and -12 over 2 is -6, right? And then -6 take away 6 is -12. So all of this is worth -12. So I'm just going to rewrite it now and replace this with the -12 that it's worth. And I forgot my little -1 there. And now this says I should go to its inverse function and put -12 in for x. So I'm going to do that. Erase this and just put a -12. And when I do that, I get -24 over 3, and -24 over 3 is -8. And when you take the -8 and you add 4, when you're done, you get -4. So I hope you're starting to see a pattern. So what an inverse function does is it undoes all the work that you already did. So notice when I first put 6 in, right? So we'll call this one function. When I put 6 in to G, I got this 3. And if I put 3 into its inverse function, I got back to 6. So it undid what it already did. So let's try this one. When I put -4 into G's function, just like this, and I did the math, I got -12. And then when I put -12 into its inverse function, I got back to -4. So I undid all the work, and I got back to what I started with. And that's what an inverse does. It undoes all the work, so you get right back to where you started with. So without any math, I should, if I put 9 in, I'll get an answer. And when I put that answer back in, I should get right back to 9. And then the same thing would happen with just the actual inverse function. So let's take a special look at this one. So this says I should take the inverse function and put it into the original function. So there's G, and my inverse function is worth 2/3 x plus 4. That's what we set up here. And I realized I put an F there. That should have been a G. Okay, so G, the inverse function, is replaced with what it's worth. And now this says go to G's function. All right, so here's G's function. Let me erase this 4. And I should put all of this in for the x. So I'll have 3/2, but instead of x, we'll go all of this. Okay, and then I still have the -6, and now I'm just going to simplify this. So when I take 3/2 times 2/3, that becomes 6/6, which is x. Well, 6/6, which is 1, and 1 times x is the x. And when I take 3/2 times 4, that's 12/2, which is 6. And then there's the -6. And when I'm done cleaning this up, I get just x. So here, if you put x in, then you should get x back out at the very end. Okay? And that's how you define an inverse function. If you have two functions that you believe are the inverse of each other, then when you take the inverse and put it into the original function, or you take the original function and put it into the inverse function, you should get right back to x. So what we're going to do is one more practice, and we're going to verify that these are inverses of each other. So I have f of x and I have g of x. So first, we're going to take and we're going to write this composition first. So this means that g of x should go into f of x. So what I'm going to do is just replace g of x with what it's worth. And this says now go to x in your f of x function right here and put this in there. So instead of 2 times x, I'll have 2 times this. So I'm going to multiply. So we get an x, and then we get a minus 6. And then what I don't want to forget is that I still had this plus 6 here. So now I'm going to bring that back down. And when I clean this up, I get just to x, which is what's supposed to happen. So if you take two functions that you believe are the inverse of each other and use a composition function for them, and you get to x, you have verified that they are inverses of each other, because what I put in is what I got out. So let's try the other way. This time I'm going to switch it like this. And I'm going to take f of x and replace it with what it's worth. So that's 2x plus 6. And then this says go to g's function, here's g's function, and put 2x plus 6 in for that x. So I'm going to do that. Here's the 1/2, but instead of x, I'll put 2x plus 6. And then I'm just going to clean this up. So I'm going to distribute again. So 1/2 of 2 is x, 1/2 of 6 is 3, and then when I subtract, I get just to x. So the fact that I did this twice and that in both situations I got x at the end means that these are inverses of each other. Okay? All right, I'm going to stop the video notes here because that was about 21 minutes, which is plenty long. And I'm going to ask that you come back to our Zoom classroom, and we are actually going to finish the notes together as a class. And then hopefully take a look at some practice before we're done. So I will see you in just a few seconds.